Once again, bulbs I'll discuss. So just only I give basics. So as when we get into numericals now, we'll discuss in detail once again. So there's the first one, it's called like a very popular called as KCL, Kirchoff's current law. In short, we'll call it as KCL. So what it says, the law says that the algebraic sum of current entering a junction must be equal to algebraic sum of current leaving a junction. So what do you mean by here word junction? Where the current branches, that particular word is called like a junction, that one. So here let's take that. These are the resistance. So current here will enter I1, I2, I3, and the current here it is leaving. So those which are entering, I'll take positive. Those which are leaving, negative. There's a convention. So there's a junction, G. So what is the equation now? Plus I1. Those which are entering, positive. Those which are leaving will be negative. So I1 plus I2 plus I3 should be equal to I4 plus I5. What is this summation of I1 plus I2? With I1 plus I2, I3. So this is the summation of current entering a junction. And what is I4 plus I5? This is nothing but sum of current leaving a junction. Therefore, the law at junction. Nothing but, shall I say, it's a law of conservation of charge principle only. So charge cannot be created nor be destroyed. That particular statement is what? Nothing but the Kirchoff's law. What is the KCL? It's another form of law of conservation of charge principle only. KCL is another form of law of conservation of charge principle. So what do you mean by current? The amount of charge entering per second at a junction should be equal to amount of charge per second leaving a junction. So what charge enters per second, that much of charge should leave per second a junction. Then only what happens, the charge will be conserved. Otherwise, at a junction, the charge will be created or will be destroyed. So what is the KCL? It's another form of law of conservation of energy principle only. That law of conservation of charge only is just put in the form of the electrical currents. Almost every numerical will be taking where all you see a junction. First of all, what do you mean junction? Where current branches. So what is the junction? Where a current branches. If current doesn't branches, though it appears like a junction, it's not. It's only a physical, not electrical junction. So what do you mean by electrical junction? Where current branches. Electrical junction, we'll write it, because physical junction, electrical junction. What is this? J is electrical junction. Current branches, it is called as electrical junction. The first law is what? We'll put like this, KCL. So next we'll go for one more, Kirchhoff's voltage law. Kirchhoff's this is the you can solve almost many numericals with the help of this, because I don't want to restrict you. So you can cover maximum numericals this week, because next week we have the depth of concepts like potentiometer, meter bridge, ammeter, voltmeter, EM of FSLs, all that one. So where their concepts are more. So again, if I bring KCL, KVL, no, it'll become clumsy for you. So many different things at one place. So that's why this week only we'll try to cover maximum circuit problem, so that next week we can put effort more on the instruments. Next week we'll be discussing more about electrical instruments. So what this law tell, like what this law says is, the algebraic sum of EMFs is equal to algebraic sum of IR drops in a mesh or loop or closed path. This is what the law is telling. The algebraic sum of EMFs is equal to algebraic sum of IR drops in a mesh or loop or closed path. We'll take this one. So suppose say this is the this is E1, R1. What is E1, E2? They are the EMF of cells. R3, E3, E4, R4. So you take, so what is it, this one? So I just connected cells and these are small tiny LED bulbs. If you're finding really very difficult, sir, what actually I'm learning. So these are some different Duracell, Eveready, Nippo, like that, no? So different cells are there, no? Those things is what I'm connecting it. And what are that resistance R1, R2? They're small LED bulbs. You can have like this. This is what we're discussing. So now, what is my question like? What about the current through the branch? So how much of current is flowing for this? So I do take help of the KVL, that one. So here I'll in what direction the current is flowing, in any direction. You assume, solve it. If you get positive, you assume in right direction. If you get negative, you assume in opposite direction. Then some conventions is what I'm going to follow it. So what are the conventions? Like across a resistor, across a resistor, across a resistor, if I move from positive to negative, there's a direction of traverse. What is that green color arrow? It's a direction of traverse here. And I'll take some other color. Later on I'll bring it. So there's a direction of traverse. So what is that green color arrow indicates? Direction of traverse. And what is the resistance? Is R. I'm moving from positive to negative terminal. No? So this is called like a fall-in drop. And you should write it as minus IR. Similarly, across same resistor, if you traverse from negative to positive. No, you can say that one, sir. We'll determine that from where I'm moving. We'll determine this plus minus, the direction of current. Current here, it enters, the where it enters, that end should be positive. Where it leaves, negative. Any reason for that? What is this conventional current? No? And what is the conventional current? It's like a displacement of positive charge. And go back to electrostatics. Positive charge, if it's set free in an electrostatic field, it will move from higher to lower potential. And what is this current? Conventional current is due to positive charge, we assume. So definitely it is moving, means it must move from higher to lower potential. So therefore, the end where current enters, that is positive, where it leaves, negative. Similarly, this is a resistor. So the direction of traverse is like this. The arrow is direction of traverse. So whatever the current will flow in same direction. So it enters this end. So positive, it leaves negative. No, this is called like a rise in drop. Now, what about that green color arrow? We ourselves, the external agent, ourselves. When we are writing equation, I can move towards right, towards left across resistor. No, this is called like a rise in drop plus IR. Now, across a cell, EMF of cell is E. If I move from positive to negative terminal of a cell, then here what happened? This should be called as fall in EMF. Now, what do you mean by fall in EMF? What do you mean by EMF? Electromotive force inside an like a chemical reaction will occur. Because of that, the charge there will experience a force. That particular thing is called like electromotive force. So I should call fall in EMF when I move from positive to negative terminal. Similarly, this is cell, EMF of cell is, so what you should write, you should call this as fall in EMF minus E. This will be right in, this is a convention. To write, to use KVL, I'm introducing convention. So this called like what is this arrow? Direction of traverse. So this is now will become rise in EMF plus C. I will, now I will traverse it. I'm going to, we don't get, okay, I'll come to the direction of traverse. So here, what is this green color arrow? Direction of traverse. Means you are here and you'll start moving. You'll go around the path. No, some shall I say loop is there. Where you begin, you are going to end up at the same point. So shall I call loop, mesh, or closed path? Okay, let's come for the current. So let's assume the current. What is the direction of current? I'll assume current in this direction. Sir, how are you sure? I'm not sure. But current, there are only two possible directions. No? What are two? Either it should be clockwise or anti-clockwise. Will I agree? There are only two possible paths the current can flow in this particular circuit here, closed path, either anti-clockwise or clockwise. Let me assume any one direction. I solve it. If I get positive, I assume right direction. If I get negative, I'll change direction of flow of current. And what is this green color arrow? Direction of traverse. Now let's give the convention. According to the where current enters, that end should be positive. Where it leaves, negative. Only for resistor you have to give polarity, not for cell. Here it enters positive, leaves negative, enters, leaves. So here enters and leaves. Now write KVL equation. So when you're writing KVL equation, what you have to follow? I'll start from here. Let me give name A, B, C, D in mesh.
Sir?
Yeah.
Sir, how did you assign positive and negative terminals to the resistors, sir?
From electrostatics, positive charge from where to where it will move, from high to lower potential. And what is that current I? Is a conventional current opposite to flow of electron. The electrostatics is very important. I'm telling this one. Delta V equal to E into delta X. That's what I'm using here. In uniform electric field, what is the potential difference? Electric field into distance, and how that electric will be directed from higher to lower potential. In mesh ABCD, I'm going to write equation. I'll move from positive to negative terminal. No? So minus fall in drop minus IR1. Then I'll move from negative to positive terminal. And I'm moving like this. Are you able to see? I'm moving from positive to negative terminal of a resistor. So fall in drop minus IR1. Then across the cell from negative to positive terminal. So if I move from negative to positive terminal, so is it a rise in EMF or fall in rise in EMF? So therefore, what should be this? This should be the plus C1. Then across this, I'll move like this, no? So I'm moving from higher to lower potential, fall in drop. So minus IR2 across the cell. Again, I'm moving from positive to negative terminal, fall in drop. Are you noticing plus C1 minus C2? How you traverse, and what is this arrow? The direction of traverse. Now again come for this across the cell. I'm moving from negative to positive terminal here. So this should be plus C3. Across the resistor, I'm moving from positive to negative terminal. So fall in drop minus IR3 here. Fall in drop symbols E4. Now here fall in drop minus I R4 plus E4 equal to 0. So therefore this will become E1 minus E2 plus E3 plus E4 should be equal to I R1 plus I R2 plus I R3 plus I R4. Look at this. I think the statement is correct. No, algebraic sum of EMFs should be equal to algebraic sum of IR drops in a closed path. That's what this equation. So what is the expression for I now? The expression for I should be equal to E1 minus E2 plus E3 plus E4 by R1 . So I'll solve if I get I negative, change direction of current. You can change the direction of current. So this is what the KVL says. These conventions are very important. It's a convention, you can't change it. You have to accept it. And you have to follow this one only. The whole in electrical technology, there's a basic convention. These are basic fundamental laws, KCL, KVL, where we'll be using to solve the problem. Anybody having doubt, you can just express it. I'll go now the application part. Any number of cells. I took 4 cells, no, any number of cells.